Okay, so how's everybody doing? Looking forward to the end of the semester? So for most of you, this is your first semester in university. How's it going? Everything's okay? So you come to class, which helps. Sometimes it feels like it doesn't, but in general, it is a good idea to come to class. Even if all you're going to do is zone out and think about something else, it's still not bad to be there to to help absorb, by accident, any information that's passed to you. Okay, so this is our last real class. So we'll have sort of an exam prep class on Monday. But this is the last time we'll really do anything. So we're sort of wrapping up now. I'm gonna use today to use a Robocode example that teaches you a few miscellaneous things. Some of them are about Java, and some of them are just about well, not computer graphics, but geometry, I guess. And then we'll wrap up with teaching evaluations. So what do I want to say? Well, I just we should stop at this point and think about this course and what we've learned, and whether we learn the things we're supposed to learn. So this is supposed to be an introductory programming course. I know a lot of you have had programming experience before. I don't think there were too many of you who actually had worked with Python before. So even if you had not, even if you had programming experience before, well, at least and you knew all the other material in the course, at least now you know another language. But even if you did have programming experience before, I don't think you knew, and even if it was in Python, I don't think you knew all the material in this course. So if you look at some of the things we've studied, we spent a couple of weeks really doing the basics, which were things like numbers, strings, and arrays, and iteration over arrays, and while loops, and if statements, and so on. So those are pretty much the basics of any programming language. But then things started to get maybe a little more advanced, and a little bit more general. So we learned exactly how to make all those constructs in Python. But then we started looking at things like objects. So how to model your application as a collection of objects, or at least if you have an application, how to pick out some objects in that application that you could use object-oriented programming for. Something probably that I think was new to most of you is the use of data structures for efficiency. So, for example, we learned that sets and dictionaries are really useful and really fast for certain kinds of operations. For sets, for example, for checking if something is in the set, and dictionaries for mapping values onto keys in an efficient way. And I'm sure, you could have done all of those things before, but you may not have known that actually, just using an array is not a great way to do it. So if you have a set of 1,000,000 elements, storing it in an array and then using that to check if things belong to the set is not very efficient. And the same thing with dictionaries. You can store an array of key value pairs, but when you want to look something up, it's kind of slow because you have to go through the whole array looking for a specific key. So we learned about that stuff. We also looked at recursion, which is in just about every programming language. So we saw how to solve some problems recursively, and we also saw some of the pitfalls of using recursion. So things like stack overflows, where you have a recursion for example, that works on arrays, and it has a recursion depth that's the length of the array. Well, in Python, for example, you can't handle an array of length more than 1,000 that way, at least with the default settings. And if you start fiddling with the default settings, you risk the chance of breaking the interpreter, in that a crash isn't now just an exception that gets thrown in Python, but actually the whole environment crashes. And we also saw algorithmic efficiency questions. So we studied why binary search is so much faster than linear search. So for example, binary search, if you use it on an array of length 1 million, will do about 20 comparisons. Linear search will do about 500,000 comparisons. So there's a big difference there. The classics we studied were sorting, so how to sort arrays. And you know, there's some basic introductory naive algorithms like bubble sort and like insertion sort that basically, well, they run in time which is quadratic in the length of the array. So if the array is of length 1 million, well, they run in time that's proportional to 1 million times 1 million, which is 1,000 billion. So they're not terribly fast. Even if you try and insert some optimizations in bubble sort, we tried to see if we could speed it up by checking to see if the array was already sorted, or if it, if there had been any changes. Realizing that the largest element bubbles to the end at each step, so we don't always have to go to the end. But still, that doesn't help much. And then we saw merge sort. This divide and conquer algorithm splits the array into 2 equal parts, sorts the first part, sorts the second part, and then only has the easy problem of merging two sorted arrays into a single sorted array. And the running time of that wasn't, for an array of length n, it wasn't n times n, it was actually n times log of n. So now if you think about an array of length 1 million, that means it's something like 1 million times 20 instead of 1 million times 1 million. And I don't think too many of you had really studied algorithmic efficiency that way. So this is sort of setting you up for a future career, well, and the next 3 years of thinking about problems this way, and thinking about solving problems, not just about getting the right solution, but getting it quickly. And that can be the difference between a piece of software that is really nice to use and a real joy, versus a piece of software which is frustrating for users, which they will switch to something else as soon as something else is available. And you've probably experienced this yourself, that you're using some software for a while, it's kind of slow and it's kind of clunky, you don't really know why, but now you can start thinking about why that might be the case. And then eventually somebody else shows you, oh, there's this other software and it's much, much nicer. It does the same thing, but it's just much cleaner and much faster somehow. And that's usually because there's been some care taken in the implementation of the underlying algorithms. If you've ever used, for example, photo organizers, it's the one that I use a lot, is photo management systems. So there are things like Adobe's Lightroom that has photo management built in. So Lightroom is a $300 software product. It's $300 a license, and it is just painfully slow if you have a lot of images in your library. And I have a digital camera that I've taken something like 50,000 photos with in the lifetime of that camera. Not all of them are good, of course. But it's just painful to use Lightroom, so much so that I end up actually, unless I need to do some serious editing, I end up just using Google's Picasa software. Does the same things. It's not as good an editor, but it can manage huge amounts of images very, very quickly, very, very smoothly, and really that's, it's a less featureful software, but just because it seems to be using better algorithms and data structures underneath, it's the one that I choose. and it's the reason I choose not to pay $300 for Lightroom. So keep that in mind, that these aren't just, you know, toy questions that come up when you're taking a course, but this can be the difference between your company's software being successful and being largely ignored by users. Okay. So that's sort of a recap of the course, and on Monday when we do exam prep, we'll sort of go over some of those topics again, and we'll also see what the breakdown of the exam is in terms of roughly the fraction of the exam that's devoted to different kinds of questions. Yep.
How is the Robocode assignment being just because the guidelines aren't too clear about what?
So do something, make a robot that doesn't crash, and I mean crash as in the code for the robot doesn't crash. It does something that's not just a copy and paste from one of the existing robots, and you know, has maybe some thought behind it. So in your README file, you know, say something about you know, what it is that your robot's trying to do. So and maybe even why that might be a good strategy. So yeah.
If we have it that we couldn't actually end up implementing what we were trying to do, but we have it in the README file, and we sort of have the general.
Yeah. So then explain where it fell apart. Yes. So in the README file, say the robot that I was trying to make was supposed to implement this strategy, but I had problems, you know, I don't know, converting from these coordinates to, you know, relative bearings to absolute coordinates or whatever. So explain what went wrong, and then maybe explain why the robot is behaving the way it is because of that, instead of what it's supposed to do. But this is actually an interesting, designing these robots is an interesting problem, because you think of some strategy, and then you start to implement it, and you know, there's, depending on how complicated your strategy is, it may not be that easy to implement. And the worst thing about it is, you may get it all implemented after, you know, great effort, and then realize, oh, actually, that's not a winning strategy after all. There's some other robot that just kills this thing easily. So it's sort of a thing that you want to think a little bit carefully about your strategy before you spend too much time implementing it, because it might not work out. But I don't care for this assignment. If the strategy is not a super winning strategy, that's not a big deal to me. If you implemented it correctly, that's great. And there was some reason that you thought maybe it should be winning. So I actually uploaded a robot with the source code today. And so all I'm going to do this class is basically talk a little bit about why I made that and what my design decisions were. So the first sort of thing that I noticed after playing with this for a while is my first robot. So if you remember my first robot, what it does basically is it goes forward, spins the gun around 360 degrees, and then goes backwards, spins the gun around 360 degrees, and then it has a couple of other rules in case it gets shot or it runs into a wall. And anytime the gun happens to be pointing at some other robot, it takes a shot. So it just goes forward, backwards, taking a shot usually at either end of that thing. And so if you start, you know, designing a robot, first thing you realize is actually this one's kind of hard to beat. I mean, it's not really hard to beat, but just your first robots usually lose to this. And so it's kind of effective, this strategy, and I wanted to sort of understand what was good about this this strategy, because it's so simple, and I don't want to spend a great deal of effort implementing something complicated. So if we compare that to, oh, I don't know, crazy or something. So see, it just goes back and forth, gets shot, he does something to run away, but normally just goes back and forth. And sort of what's effective about that is, well, he's consistently taking a shot at something, pretty much once every round. If you turn the gun 360 degrees and there's any other robot on the board, you'll spot one. So you shoot once in a while. And he's never really standing still very long. So sometimes someone takes a shot at him, and he's gone by the time the shot arrives. And that's particularly true. So he's getting unlucky here in that the other robot ends up being in front of him or behind him. So moving ahead or moving backwards isn't actually running away from anything. Well, it's running away possibly, or it's running into something, but he can't move as fast as a bullet, and so so he won there actually. So running directly away from a bullet is not a good idea. Same thing with falling trees, and yeah. So there you go. Same thing if you're being chased by somebody in a car, right? You don't try and outrun it. Just step to the side, or run behind a tree, but then get out of the way when the tree falls over. Okay, so yeah. So if you look at this strategy for a bit, you realize, well, it could be a little bit better. Well, it could be a lot better, but how could you optimize this? Well, one thing that's where this moving back and forth strategy is really effective is if the other robot is orthogonal to you. So if the other robot is here and you're facing 90 degrees from that robot, then moving back and forth really makes it hard for them to hit you. On the other hand, if the other robot is directly in front of you, then moving back and forth means you're just getting closer and further from the other robot. And so the idea that I had was to actually try and turn yourself 90 degrees, orthogonally to whatever you happen to be aiming at. And the other nice thing about that is, well, if you're 90 degrees from something else and you're moving back and forth, well, every time you go back and forth, you'll actually, well, if your gun is also 90 degrees to you, you'll actually see it. It'll be in front of your gun for a section. You'll get a shot off and then be gone by the time it gets to return fire. So that was the idea. So let's see how to implement that. So we open the robot editor. Let's make a new robot. We'll call him Angler. And I want your robots in the Comp 1405 package, so they're easy to find. Okay. So Angler is going to do a couple of different things. So he's going to be operating in different modes, and so he'll want some variable called mode, and that variable should be able to take on some different values. And so one of the things you can do in Java, well, we've seen a few of these, but it doesn't matter, is you can define static variables. And these static variables are variables that are not specific to a particular instance of a class. So, so for example, I'm going to define a variable called scanning. So one of the possible modes is scanning. It's maybe the integer 1. And there's no reason that I need a different variable scanning for every different robot, because every different robot treats scanning as the number 1. It's just really a constant. It's a number 1. And actually, something else you can do in Java, if you don't want a variable to be changed, so you declare it static. That means it's shared among all instances of this class. You can also declare it final. And final means that it won't be changed, or it can't be changed. So it's assigned at the time it's created, and then it's not changed. Something else that I'm going to, so scanning is when my robot is sitting still and its gun is turning 360 degrees looking for a target. When it finds a target, it will be in a different mode. It'll switch to hunting mode. And hunting mode is when it turns itself 90 degrees from its target and then moves back and forth trying to shoot at this thing. Okay. And there's another thing that actually, if you watch a few of these robot battles, you'll realize that for many of these strategies, they become problematic if your robot gets stuck in a corner or gets stuck too closely to other robots. So if it gets pinned in a corner, these things generally don't work. So moving back and forth means you'll just keep running into walls. And so we'll have another mode that we'll deal with when this happens, when we hit a wall or get stuck in a corner. We'll panic and try and get out of there. Okay. So there's 3 modes. All right. So of course now the most important thing we should do is pick some colors for our robot. This is absolutely the most important part of the process. And I don't like the colors that happen to come with AWT, so I'm going to make my own colors. So where am I going to go to find colors? Well, I'll go to the internet. Picking colors is difficult. So luckily, there are designers out there. And actually, there's a whole theory of how to select colors for things like web applications, or actually graphic design in general, and certain combinations of colors that work or not. So we have this robot that has 3 parts. It has a gun, it has a radar, and it has a body. So we want 3 colors, so we can use a triadic color scheme. And so this particular tool lets you pick basically the primary color, and then it gives you 2 colors that are a good match for that one. Okay.
So it finds the complementary colors for you?
So it finds the complementary colors for you. Well, they're not complementary, they're, so complementary would be sort of exactly the opposite,
Yeah.
but then you only get 2 colors. So this gives you a triadic scheme, sort of an equilateral triangle in the wheel of colors, or not equilateral, isosceles triangle in the wheel of colors. So these 2 are, sort of complementary, and then as complementary from each other as they can be. Complementary one would be in the middle. These are on the opposite side, and they're also far apart from each other. So what do we want as a primary color? Something flashy? Purple? No. It's good. We'll. All right. So so here's the first thing. It tells us the colors. It says this is color D3006B. Okay. Does anybody know what that's referring to? Yeah, coordinates, yeah. It's the hexadecimal code for the RGB, the red, green, and blue values of this thing. So we didn't discuss number systems, and that's something you'll learn about a bit later. But hexadecimal is a number system where you have 16 digits, 16 possible values for digits, 0 through 9, just like we're used to, and then A, B, C, D, E, F as well. And so it turns out that, remember RGB values were, there were 256 different RGB values. Well, when you express that in hexadecimal, that's 2 digits. So if each digit represents 16 values, then 2 digits can represent 16 times 16, which is 256 different values. Okay, so if you go and read the documentation for AWT's color class, you'll see that you can create a new color by specifying the 3 red, green, and blue values. And so we want D3006, is that 8 or B? That's an 8. Okay, D30068. D30068. So okay, and this is something in Java. I think it's also in Python. There's different ways of expressing integer constants in Java. So there's the usual way where you just type it in as a decimal number with the digits 0 through 9. But if you want hexadecimal, you prefix it with 0x, and that tells Java that what's coming next is a number expressed in this hexadecimal format, this base 16 format. So this says use this red value, this green value, and this blue value for this color. Now over here, 00C1 2B. And then finally, F0 FC00. Okay, so those are our colors. Okay, can't find color, and that's because we didn't import the color class. Okay, so that compiles. Let's get our tournament set up so we know if we've got the colors right. And we call this guy Angler. Okay, perfect. That's a nice looking tank. And so this is doing pretty much the same thing as my first robot, but even dumber. And something else you can do is which is also important, you can change the color of your bullets. What's a good color for a bullet? Pink? You want to go with this thing?
No,
Better pink. Okay, better pink. Better pink. I don't know. Where do you...
Yeah.
That's a good bullet color. F97083. F97083. Okay. So now we're good. Pink bullets. There you go. Perfect. All right. So that's all set up. Now we have this instance variable for our robot. It's shared it's for this particular robot, so it's not static, which means it's for this robot only. It's not shared by every robot of this type. So it's not shared by every instance of this class. It's specific to this class. And so before we start our main loop, we should decide what mode we're going to start in. So let's start by looking for other robots. Okay. All right. So here we are now. This is the main loop. This is the default behavior when nothing else exciting has. I really hate this editor that comes with this, by the way. That when nothing else special is going on, this is what we're going to do. So we have three possible modes, and so they're each integers, and the way to deal with that kind of thing in Java is to use what's called a switch statement. And a switch statement is basically it does the same job as a bunch of if-else statements that are all cascaded. So if mode equals scanning, do something. Else if mode equals hunting, do something. Else if mode equals panicking, do something else. So switch statements were designed exactly when there's one variable that controls which of the cases you fall into. And they're broken up into cases. So the cases were scanning, hunting, and panicking. And I'm not sure if I like switch statements or not, because they're easy to make mistakes in. So you specify the cases that you want to have in your switch statement. And now the value of mode will decide which of these cases you get executed. But the thing you have to look out for is, for example, once I'm done executing a case, like this scanning case, if I don't break at this point, the code will just fall through into the next case. So then it'll start doing the hunting case, which is not what we want. So there you are. In any case, so if we're scanning, so that means we're looking for other robots. So an easy way to do that is to turn the gun, let's say, right 360 degrees. That will find another robot. Okay. And if we're panicking, then maybe what we'll want to do is, this function go home isn't defined yet, but we'll want to go somewhere safe on the screen, or not safe, but at least central, where we're not stuck in a corner or trapped on a wall. So we need to define a method called go home. And that's just for us to use. So we'll make it protected. Doesn't need to return any value. And we'll fill that in later. But for now, it'll do nothing. So now let's think about this hunting. So hunting is when we have found a robot. Our gun is currently pointing at that robot. And in fact, we've already turned the tank 90 degrees. So the tank is now 90 degrees from the thing that we're hunting. So what did I say we do then? So here's the thing we want to kill. Maybe it's sitting duck, and we're now 90 degrees to that. We want to start going like this, back and forth. So what does that translate into in robot language?
Forward, backwards.
Forward and backwards. So. Yeah, so we can't go side to side. We have this wheeled robot that only goes forward or backwards, but before we start hunting, we'll turn ourselves 90 degrees to the victim, or the prey, I guess. And so what we want to do is, let's say, ahead, let's try 150, and then back, 150. And we know that there's these events that happen. One of the events is when there's something in front of your gun, and so we don't have to handle that in particular. And maybe it's not 150. Maybe we want to go back. No, let's say 150. We'll see how to deal with that. And one of these events is when something is standing in front of your gun, in which case that's when we'll figure out what to do. All right. Okay, so here's this on-scanned robot event. It means we have seen a robot. This is where we want to do our stuff. So let's see. We've seen a robot now. What we do next depends on what it is that we're doing exactly. So if we're currently scanning, that means we want to get ourselves now set up to kill this thing. So let's say if the mode is equal to scanning, then let's stop and get everything lined up. Maybe we'll fire off a shot just because we can. And now if you look at the robot documentation, the robot API, so right now our gun is pointing at this thing, or at least pretty close to it. So there's actually a flag you can set called set adjust gun for robot turn. So what that says is, or what this flag does, it's either true or false. It controls whether or not the gun and the robot turn independently. So if this is true, it means when I turn the robot, the gun will stay facing in exactly the same direction. And if it's false, when I turn the robot, the gun will turn with it. So the gun is mounted on top of the robot. So it says, so true means turn the gun at the same time you turn the robot, and false means don't turn the gun at the same time you turn the robot, which in essence means that the gun follows the robot or doesn't. So we want the gun not to move as we make this turn, which is going to take us 90 degrees to our robot. Now we'll do something really simple. We'll turn right, and we want to turn so that we're 90 degrees from the robot. So we need to get their bearing. So if I turn right by get bearing, so we should probably bring up the documentation. And the event was on scan robot. So we've got this scan robot event. And it has this method called get bearing. And this is a lot of the things, actually, a lot of the difficulties of robotics have to do with working in different coordinate systems and translating from one to the other. So you really have to read this documentation carefully. It says that it returns the bearing to the robot you scanned relative to your robot's heading. And it gives you a number that's between minus 180 and plus 180, which basically, so if this is positive, it means the robot is on your right-hand side, some direction, and if it's negative, the robot is on your left-hand side in some direction. So if we turn right by this amount, then we'll be facing directly into this robot. So we can actually check that that's true. So we scan, if we turn right by that amount, I think we'll be facing directly into that robot. And then let's say mode equals, we'll just set mode to panicking because we want to stop and pause and see what happens here. So we build that. Looks like we've got a bracket error there. And a good one for testing against is sitting duck, of course. So now our robot should find this thing, find sitting duck, and then face it. Oh, there we go. There you go. Finds him and faces him. Finds him and faces him. So notice we turn, the gun stays not turning, but we turn this and turn and face it directly. Now we don't want to face it directly, we want to be 90 degrees to it. So we'll do it that way. There. So now we turn 90 degrees. And we're in a good position now. This is exactly what we want, or it's almost what we want for hunting. And what do we do when we're hunting? We go ahead 150 and then back 150, which is not quite right. To start hunting, we would like to go back 75 to start with. So we turn 90 degrees, we back up half, 75, and then ahead 150, back 150, ahead 150, back 150. So let's see if that can beat sitting duck. Forgot to compile, maybe. There we go. So he scans back and forth, back and forth. Exactly what we want, but we need to shoot at this thing. So if the mode is scanning, then we adjust ourselves and then turn the mode to hunting. Something we should be careful of is, actually I don't know if it matters. We'll leave that off and see what happens. But if we're not scanning, well then we're either panicking or we're already hunting. We should just fire, not waste this opportunity. So there, that's exactly what we want, right? So we shoot this thing until it's dead. If he was returning fire, he would have a hard time. So let's try a slightly more challenging opponent. Ramfire is a real jerk, actually. Is very difficult to beat. Tracker, sure. Tracker.
Ramfire just rammed you in my sheets.
Yeah, Ramfire just basically drives into you as hard as it can and shoots you constantly. It's really tough.
You can't teach it. Well, the tracker does like the same thing. Except he just moves.
The tracker doesn't try and ram you. He just tries to get close enough to shoot you.
No, but he still.
And indeed, so here we've got bloop, bloop. Let's try another round. Angler versus tracker. So tracker is not so so good against angler. And really, it's not good precisely because of the strategy what we're thinking of is usually by the time tracker gets a shot off, we've moved before the bullet actually reached us. And tracker is also very non-responsive to being shot, which is not good for him. So now we see we never did implement that code for panicking, and so we see what happens when we get stuck up against the wall. And here's something else. So what exactly are we doing here? For a while there, we were just driving back and forth with nothing in front of us. We didn't go back to scanning. Right? If we look at the transitions we take, when we scan a robot, we go into hunting mode. And when we're in hunting mode, that's it. We go ahead, back and forth, back and forth, back and forth. So, when is it a good idea to stop hunting?
When there's no longer a robot, we go back and forth.
Yeah. So let's say we've gone back and forth and we didn't even see anything because maybe the reason we stopped, that robot died or is gone or whatever. So so if we didn't see anything, then we should, maybe go back to scanning again. So we can control that again with some variable that says, I don't know, let's say saw something. We'll set that to false. We'll go back and forth. And if that's still false, then we should stop this because we're just wasting time going back and forth doing nothing. And we'll say we'll go back to scanning. So the next time we go through this loop, we'll go into scanning mode. We'll turn the gun around.
You do brace brackets after the testing?
You don't actually, because it's only a one-liner. So remember this nice, not necessarily nice, but this weird thing about Java and C is if you only have one line after a conditional statement, you don't need the braces around it. Okay, so it says there's no variable called saw something. So let's think a little bit about what we want saw something to be. What kind of variable? It's going to be a Boolean, but what should the scope of this variable be? So should it be only for this function? Should it be for the object so that it can be changed by any of the functions that operate on this object? Should it be for the class so that it's one variable for every instance of the class?
It should be just for hunting. It depends on whether we want to use it for something else.
Yeah, but so if you look at this code, somehow we're assuming that saw something can change from false to true in between this line and this line, right? And so that means it's got to be changed by some other function, which means that it's really something that's associated with this class. It's not only for this function. So we have this Boolean variable called saw something. And of course, different robots shouldn't share the same variable saw something. If we have two of these robots, they shouldn't be sharing this same variable. It doesn't matter if some other robot saw something. It's if I saw something that I want this. So we have this Boolean called saw something. And now, when do we see something? Well, when we've scanned a robot. So that's when we set saw something equal to true. So Angler's going to shoot for a while. They're both going to pick on sitting duck. So notice at some point Angler didn't see something, so it actually did another scan. And Tracker's having a very hard time right now. Tracker's dead, and we had to do another scan to get back to him, but that got him. Okay, so still the weakness of this thing, and it's even showing up a little bit here, is when it starts running into a wall. That can be a problem. And so this sort of strategy of moving back and forth on a fixed path works well, provided that you don't get pinned into a corner like this. So here we somehow drove ourselves into a corner, and and we're sort of stuck here. Okay. So so this on hit by bullet, let's not even worry about what happens when we get hit by a bullet. And this on hit wall, this is one that we don't like. So if we hit a wall, we'll maybe switch to panicking, which means we'll try and go home. And so now let's see how we go home. Well, if you look up the methods that are available in Robot, you can get the robot's x coordinate, and you can get the robot's y coordinate.
What is it relative to?
So 0, 0 is down here, the bottom left corner. So y coordinates go up. So it's like the Cartesian plane that you have in, well, you know, algebra or whatever, geometry, regular math. So the origin is down here. And all the coordinates are positive. So if you have a negative coordinate, you're off the map, which is impossible. And you can also see that there's a method called get battlefield width. So the coordinates go from 0, 0 to the width, which is this corner over here. And really what home for us will be the center of the screen. So we'll go divided by 2, and you can also get the height. Okay. So we're currently at coordinate x, y, and to go home we would like to actually go to x0, y0. This is where we would like to be. Well, one thing we can do is compute the differences, I guess. See how far we'd like to move in each of these directions. So the delta x is x0 minus x. The delta y is y0 minus y. And so basically here's the picture we have now. There's the center, x0, go away. Y0 we want to get to. There's this x, y that we're currently at. And we know delta x, and we know delta y. What do we do from here? Yep.
Don't we need to switch the angle that we're at, so that way it's along the, like in between the two points.
So we would like to have our tank, so turn our tank, our robot, so that it's pointing to where we want to go, right?
Yeah.
How do we do that?
You have to get the angle that we're at.
So we'd like to know, well, there's a few things we need to know, but the coordinate system for this thing has, this is 0 degrees. Over here, let's just draw it off to the side, 0 degrees. So it's like the coordinate system you see on a map, 270 degrees there. And 360 is back to 0. So what we really, there's a few things we want to know. It also depends where we're facing. We'd also like to know this angle. We have to compare that to what angle we're currently at. So we need to know an angle here. Actually, any of them will do. Pretty much any of the angles in this picture will do. One that is fairly standard is, in normal mathematics, when we're measuring angles, they're usually measured with respect to the positive x-axis, right? So, does anybody know, if I want to know from 0, 0 to xy what this angle is? Anybody know how that's done?
It's going to be your opposite, your sum, which is Is it no trig?
Well, Java has a math library that does some of these things.
What's supposed to say that?
So what kind of coordinates do we want to switch to? We're currently looking at something in Cartesian coordinates, but really what we want is yeah. Yeah, so that's the inverse tan is what we want to use, but actually even that's not enough because it has problems. It only gives values between 0 and 180. But so nobody's learned about polar coordinates? No? Okay. So polar coordinates are just another way of representing any point in the plane by measuring two things. This angle theta and this distance here, r. So there's two ways to represent, well, there's lots of ways to represent any point in the plane. One of them is, the usual way with x and y coordinates, but for every point that has a particular set of x and y coordinates, it can also be represented by giving this angle formed with the x-axis from 0, 0, and then the distance from 0, 0. So those are called polar coordinates. I don't know when you're going to learn about those now, because I used to learn about them in high school, and then we used them here. But hopefully these will not get lost because they're fairly important. But if you go and look at the math library in Java, there's a method called atan2, which takes the y-coordinate and the x-coordinate. Notice that they're reversed of the point, and it returns the angle theta from the conversion xy to polar coordinates. So theta is the angle with the x-axis. Okay. Now, now there's a few things going on. So one is, so we want to use atan2, and so we've basically made our x-coordinate and y-coordinate the origin, and dx and dy then is the destination. So we want to pass in these two arguments, dy and dx. But this is a math library, and regular mathematics doesn't work in degrees. It works in radians, so multiples of pi. So we have to multiply by 180 and then divide by pi. Well, we can, but eventually the robot library uses degrees, so we have to convert that. What's worse, more troublesome for us, is 0 is different, right? Normal math, this is 0, and this math, this is 0. What's even weirder, more troublesome, is in normal math, the angle increases as you go counterclockwise. In this coordinate system, the angle increases as you go clockwise.
So we just minus
So the,
and then do then multiply by -1.
yeah. So this minus sign will take care of the fact that they increase in opposite directions. And then to fix the issue with the coordinates being different, with the origin being different, you start by taking this value and subtracting it from 90.
Why is it this way? Why isn't it regular math?
Well, I don't know. No, because it wanted to be familiar for people who know. I guess it wanted to be familiar for people who know about reading maps and things. You know, if this were a military people doing something with these, well, they would be working in degrees, compass headings. So I wanted it to be, familiar to people who work with compass headings, which makes it awkward to do these conversions from x coordinates to from xy coordinates to these directions. Okay. So that's the direction we want to head in. Okay. And no, I did not just do this off the top of my head. It took a couple of tries, but I have it written down here. Okay, and that's interesting. So then let's turn right. Oh, yeah. So that's the direction we want to go in. Now the problem is we can't just say turn to that direction. We have to express the direction we want to go in, or we have to say turn some number of degrees. And for that, it matters where we're heading, which direction we're facing in. So really, the turn that we want to make is the direction we want to go in minus the direction we're currently facing. Okay. Great. So hopefully that will point us home. Let's just check that. Where are we? If we start out by panicking, then we should just go straight home. There. So now we've turned to face the center of the screen. Let's check to see if that works again. Yeah, we turned to face the center of the screen. So, anybody know what's happening there? So we turn to face the center. It's actually a numerical rounding error. So we turn to face the center, and then we do the same calculation again, and the calculation tells us now to turn 359.9999 degrees right, which we do again, which then tells us to turn 359.999. So it's just a rounding error, which will go away in a second.